Good afternoon, everyone, and welcome to our first TEESMAT webinar. First of all, let me introduce myself. I'm Agata Papotto, and I'm a project manager at EBN, the European Business and Innovation Center Network. I have recently joined the TEESMAT team, and I have supported the organization of the webinars. The TEESMAT project organizes a series of webinars with the service providers presenting the validated characterization techniques and the user cases. For the first webinar today, we have the pleasure to have with us Dr. Anass Benayad, who will present a session on photoemission spectroscopy applied to storage energy material. Anass will be leading the main session of the webinar, and if you have any questions or comments during his presentation, please feel free to share them in the chat box, because we will have a Q&A session right before the end of the event. Just before we get started, I would like to give the floor to our project coordinator, Fabian Verdu, who will give us some background information about the TEESMAT project. Thank you.
Thank you, Agata. So I'm Fabien Perdu. I'm from CEA, which is the coordinator of the TEESMAT project. And I will try to be very quick in order to leave as much time as possible to Anass. So TEESMAT is a European project funded by Horizon 2020. And it's an open innovation testbed for electrochemical energy storage material. The idea behind TEESMAT is that the European battery market has a very quick growth, and the development of a competitive battery value chain in Europe is one of the top priorities. In order to do that, it is needed to have a progress in electrochemical storage, and it depends on characterization and understanding of all the basic processes. This understanding needs advanced techniques, which are already developed by a European research lab, but underused by the industrial companies for the moment. So in TEESMAT, Anass, please. Yeah, thank you. So in TEESMAT, our aim is to provide an easier access to those advanced characterization techniques and services in the field of electrochemical storage. So there are three goals. The first one is to set up the testbed, the platform. The second one is to demonstrate its added value by solving persistent high-impact problems with concrete examples. And the third one is to ensure the growth of the platform, its longevity, and its financial sustainability even after the end of the project. So we have various kind of partners in this project. We have 8 service providers who are laboratories or also companies providing characterization techniques, which allow to dig into the chemistry, the morphology, the structure, the performance of the materials, and also to do some modeling. And we have also 10 service users. The service users are industrials from the field of materials and batteries, and they come with their questions, which are called user access cases. And we have a very special partner with CERMA, who will be the single entry point from now and after the end of the project. It means that when a company will have a question with a need for characterization, CERMA will be their entry point and will redistribute the question to the right laboratories and techniques. And we also have a database for tracking the samples, the test, and the results. This database is managed by CEA with a very strict access control to ensure confidentiality of the data, and will allow to build the knowledge among the consortium of service providers, and also to enable the comparison between various results when this is accepted by the service users, when they accept to share some results. It will be an option which will be given to them. Okay, Anass. Can you,
Sorry.
yes, thank you. And so finally, I would like to share with you the timeline of the project. This is a 44-month project which ends in August 2022, so in 1 year, a bit more than 1 year. And there are 2 phases in the project. The first one was to set up organizing the platform. And this is finished. The second is the test of the platform. And we are in this second phase where CERMA has taken the role of the single entry point. And this is before the end of the project. After the end of the project, we begin the commercial activity where we will offer the services to any industrial who wants. And so in this second phase, we are looking for new partners, both external service providers and external service users. External service users will form the base of future customers, and external service providers can test their techniques on concrete user cases and may become future members of the commercial consortium, which can be a bit different from the consortium inside the project. So we are now in this phase where we are opening the service both for customers and for service providers. So thank you very much for your attention, and I leave Anass explain the very interesting technique of X-ray Photoelectron Spectroscopy.
Thank you, Fabien. So can you hear me very well, right? Okay.
Yes, we can.
Well, thank you for TEESMAT organizer. That I'm quite lucky because I'm the first one who will start the series of webinar. That's very honor for me. And today I'm going to talk about photoemission spectroscopy applied to storage energy materials. And in the beginning, I mean, this is the outline of my presentation. If in the beginning, I will start with short introduction of X-ray photoemission spectroscopy. And afterward, I'll just give some contribution of lithium-ion battery, or the XPS can contribute to studies such kind of technology. And I will switch to new development in the field of photoemission spectroscopy. And at the end, I would just like highlight the XPS contribution within the TEESMAT framework. And in general matter, I mean, this is like what's like the TEESMAT is going on. I mean, in the overview of physical-chemical characterization, it's a very simple way that there is like, if we consider some sample, wherever the sample is, could be like solid, polymer, electrolyte, whatever, the characterization is based on excitation wave, which could be a photon, ions, electron, or atoms. We have any kind of excitation. Through the interaction between this excitation wave and the matter, we will have different kind of interaction that can give rise to different particles, either photons, ion, electron, or atom. That's what we call the response of the secondary ions. So the idea, every characterization technique is based on this simple process. In the XPS, the excitation waves is the photon. In this case, is the X-ray. And the response is the electron, is the photoelectrons. So all those techniques can be summarized somehow in several families. We can have, I give just like simple schema of our state of art of characterization technique. We can have another way to represent our technique. There is like chemical methods and physical methods. In the physical methods, we have like more localized technique, either like at atomic level, surface, or in depth. And for example, if we look at the XPS, it's a physical method. It's more surface analysis technique. That means the depth analysis is between 1 to 10 nanometers. And in this family of technique, we can find similar techniques, but in different can give different information like Auger spectroscopy, secondary ion mass spectrometers, high resolution electron loss spectroscopy. And we can add other techniques. I will not go in detail, but just like to show you that every technique has different resolution, different kind of information that we can get. And for example, here I would just like emphasize or highlight those techniques, Raman, NMR, they cannot give like elementary analysis. So the other technique, we can do some quantification, either like qualitative analysis or quantitative information, but we can also do quantitative analysis. And this quantitative could be absolute quantitative analysis or semi-quantitative analysis. This is how we'll go further for this part. And the photo emission is, I mean, kind of, it's like a kind of wording game. Is an exciting story because it starts with the first work of Hertz, which it was the first who like proved the presence of electrodynamic waves, and the Einstein who got the Nobel Prize for the photoelectric process. In fact, the photoemission spectroscopy is based on this process, that every materials that's submitted to some more wavelength will emit an electron with certain kinetic energy. That's the principle. But to interpret this interaction, we have different framework. The first framework was like proposed by Niels Bohr, which like explained the atomic levels of electrons in terms of the planetary models. In this case, when we irradiate a photon, when we irradiate material, we will eject an electron from different orbitals of the atoms with certain kinetic energy. And this is the first approximation that can help to explain the photoemission process, but also there is advanced interpretation, which is based on Schrödinger equation or Heisenberg uncertainty. That's just a simple framework, but this is just, I want to highlight this part. And the pioneer work of photoemission will start with Seibang, which got the Nobel Prize for inventing the first X-ray Photoemission spectrometers for his contribution to the development of high resolution electron spectroscopy. And for me, we should also thank the engineer and technician that developed vacuum techniques, because the XPS without ultra high vacuum cannot exist. So those also they contribute a lot to this technology. And also we have the first works of William Lee Joly, who make a clear correlation between the core level binding energy and the chemical structure through, and in this example, this is the first paper that was awarded for Nobel Prize, where we can prove the chemical displacement of copper oxide. When we have different oxidation level of copper, we can see that the copper core level can shift depending on the oxidation state. That is just the historical background. And this is the first paper that the pioneer work when they prove that, for example, for sulfate-based material, that depending on the oxidation state of the sulfur, like for example here, the most reduced sulfur, sulfur 2-, or elementary sulfur or oxidized sulfur, that we can see clear displacement or chemical shift or depending on the oxidation state of the sulfur. And afterward, we Seibang that he proposed other analysis for polymer materials, and we can see for depending on the chemical structure of the polymer, we can have different signature when we probe the carbon or oxygen related core level. That is just like some historical background. And what is the principle of X-ray photoemission? If we look at every material is like characterized by his electronic structure. For every material, we have like core level electrons and valence band electrons and conduction band electrons and vacuum level. That is the electronic structure of every material. So the X-ray photoemission spectroscopy that consists of irradiating the materials with an X-ray, which could be monochromatic wavelength, and we eject an electron with certain kinetic energy. This electron can be ejected either from core level or from valence band. We have to keep in mind that XPS is blind to what's happened in conduction band, that we are not sensitive to the conduction band electrons. And if we take in terms of chemical reaction, when we apply some photon energy to some atoms, we will generate ionized atoms with certain electrons. The conservation energy that can combine the binding energy of these electrons to its kinetic energy. So finally, the photoemission spectroscopy can be simply expressed by this simple equation, which what we measure is the binding energy of the electron in their chemical environment. The photon energy is fixed by the instrument, and what we measure is the kinetic energy of those electrons. And this is just like surface parameters that we can neglect. That is the main schema of the photoemission process. And there is additional process that can occur during the photoemission. When we excite an electron, we will create a hole. This hole can be filled with other electrons from upper level with emission of fluorescence X. And this energy can be given to another electron and eject another electron, which is called electron Auger. So in XPS, we can either do photoemission or we can do Auger spectroscopy. That is the background. And here, what we get finally is an XPS spectrum, or XPS spectrum in this case. In the XPS spectrum, I will give later, this is kind of quiz. I will give you later what is the signature of this, what kind of material can give us this kind of signature of peak. This is the carbon 1s. That means is the electron 1s, the electron structure of carbon that was ejected through the photoemission process. So we have different information that we can probe, is the position of the peak, that's what we call the binding energy position, the full width at middle half, that can help to quantify our element. We have also the background, which is also can give some information. I will not go in this part. This part will be out of the scope of our technique, but that is the main information that we were using during through TEESMAT project, and that will explicitly explain what does mean, or every peak, how can we interpret every peak. Now we go to this peak. This is polytetraphthalate ethylene, is like what we have in every bottle, water bottle is PET. And this is the XPS signature of our PET. And the PET chemical composition, it's like this. We can see that we have aromatic group, we have carboxylic group, and we have alkyl group. And what we can link from the carbon 1s, we have the first peak at lower binding energy correspond to CH2 bonds. The second peak correspond to the CH2 bonds to one oxygen. The third peak is the carboxylic group, and the fourth peak is the delocalized electron in the aromatic group. In the oxygen peak, we can see two peak signature, one related to the first oxygen and the second related to the second oxygen. So what is the driven force in this case is the electronegativity. We can see that the first carbon bond to carbon. Since the carbon is low electronegative to the oxygen, so its binding energy will be at lower position. More the neighbor is electronegative, more the shift go to higher binding energy. So that is the way how we may link our spectra or our spectrum to the chemical structure of our materials. So there is strong correlation between the electronegativity of the surrounding atoms to the chemical structure or the binding energy that we observe in the spectrum. The second part, I give another example, is the oxidation state. Also, XPS can give information about the oxidation state of materials. Here I give two examples. Let's start with the molybdenum oxide. We can see for the molybdenum, this is 100 nanometers molybdenum oxide deposited on silicon wafer. And we can see that we have different signature. The first peak, it corresponds to molybdenum metal. The second peak is molybdenum MO2. The third peak is MO3. What we can see here, that more the molybdenum oxidized, more the shift go to the higher binding energy. By the same analogy, for here, like different vanadium vanadium oxide materials. We have vanadium pentoxide, vanadium VO2, V2O3, and vanadium, metallic vanadium. In V2O5, the vanadium in 5+ oxidation state, so it's located at higher binding energy. For VO2, we are in 4+ oxidation state, so we will have shift to lower binding energy, and more we reduce, more we go to lower binding energy. So here we can think that, for example, for battery materials, it's a redox process at the end. So what we look is the reduction of metal oxide materials. So the XPS from this example can be one of the powerful techniques to probe the oxidation state of materials through the oxidation, so during lithium insertion or de-insertion. This is another way to interpret our XPS data also is the valence band study, which is not quite used in XPS. It's not common in XPS. If we look at our, for example, the literature, there is only few papers that take care of this part of the spectrum. And here but because it needs some very advanced theoretical support. And I will give example here is titanium disulfide and tungsten disulfide. In this case, we keep the ligand is the same, is sulfide, but we change the metal. We move from titanium to tungsten. And we can see that the signature of valence band is different when we change the metal surrounding the ligand. By doing some ab initio calculation on the model structure, TIS2 or WS2, we can see that by ab initio calculation, we can produce 3 peaks here, which correspond to the 3 signatures that we have in the valence band here. When we simulate the tungsten disulfide, we have several peaks which can be assigned, which can help to interpret those different peaks in the valence band. So here we can see that the valence band can be also source of information, but it's need like advanced methodology to interpret this data. And the last part, I'm going quite fast because the main subject of this topic is to see how photoemission can help to understand storage material, but at least I need to give some background that help to understand the next of the presentation. In the XPS also, we can, through this complex formula, we can get the concentration of our element. And this formula, we can make it very simple if we consider all other parameters that can be measured through the detector, that we can link the intensity of the peak to the number of the atoms that can, from where this peak arises, and the parameter S, which is the sensitivity factor, which means the cross section. And that means, in other words, is the probability to eject an electron from certain orbitals. That parameter is very important to do accurate quantification analysis. So from this formula, simple formula, we can integrate the spectra and have a concentration of different elements. So the XPS, moreover, like additionally to the qualitative analysis, can be also quantitative analysis. And here, in terms of equipment, that's what's happened inside the spectrometer. We have an electron gun that will irradiate aluminum foil, which we call anode. We generate X-ray photon, and through a monochromator, we will shine a sample. And after shining the sample with this monochromator wave, which we can eject photoelectrons that go to the detector and acquire a spectrum. And the acronym of XPS, why we use XPS, in the beginning, when this technique started, the name of this technique was not XPS, was ESCA, which is Electronic Surface Chemical Analysis. That is the original name. But because now we can tune the photon energy, then we can give another acronym to this technique, depending on the origin of the nature of the photon we use. We can talk about UPS, which means UV photoemission spectroscopy, when the photon is below 40 electron volt. We talk about X-ray photoemission spectroscopy, or XPS, when we have a photon energy about below 2000 electron volts. and we call nowadays about XPS is high energy X-ray photoemission spectroscopy when the photon energy exceeds 2000 electron volt. And this is in the beginning, usually we can perform this in synchrotron radiation, but nowadays we have in-lab XPS, which can be equipped with two kinds of sources, chromium K-alpha or gallium K-alpha. Just to know that in our CEA nowadays, we are equipped with chromium K-alpha, which is the first HackSpace, laboratory HackSpace in France. There is another one that will be installed in Dijon, that's just like for knowledge. And just like before, to go further, just like this is the XPS at the platform of characterization in CEA, which is like a platform which can hold different technique and with different center of competencies. My center of competencies is like surface analysis center of competencies, which is organized as follows. We have different technique, which is like surface technique, including top SIMS, XPS and XPS, XPIM, X-ray Photoemission Microscope, Auger spectroscopy, and other AFM or scanning probe microscope. What is interesting here that all those techniques are connected to a glove box or clean room, and we can transfer the sample in inert atmosphere without any air contamination. That is important for battery materials. So after this overview, I will just like introduce shortly what we will talk about lithium-ion battery. This is the way how it works. Basically, in general, we have like a negative electrode, which mainly constitutes of graphite, and a positive electrode, which is cobalt. In this case, is lithium cobalt oxide. When we oxidize lithium and during the charge, we remove lithium and reduce the positive electrode materials. And in the meantime, we will form some passivation layer at the electrolyte. And this electrochemical reaction will follow those chemical reaction. At the cathode part, we will have like a reduction, and the anode part, we will have the oxidation of lithium. And the capacity can be, the capacity that is exchanged during this process can be calculated, can be linked to the mass of the active materials. And we have to emphasize different problem in lithium-ion battery. First is solid electrolyte growth. That's what is the mechanism of the growth, what is the nature of this SEI, how it's organized. This is like the first model that developed by Peled, but which this model can be, it's like, it's under debate still nowadays, because it depends strongly from the electrolyte solution, from the electrochemical condition. There is many parameters that play on the nature of and the thickness of this SEI. The second one is the dendrite growth, like in lithium metal based battery. We can have also volume expansion, for example, in silicon-based battery, or we can have redox process or metal dissolution in, for example, in high voltage material like nickel manganese or cobalt oxide or LNO materials. So all those problems are like a challenge for battery materials, and XPS can help to other with other technique can give some information. I will give three examples later to see how XPS can be helpful to understand some of those processes. And I will come back to, I will keep in lithium-ion battery, it's like very simple, but in this meantime, it's very complex materials. It's simple in the case, it's just like a negative electrode that is linked to the positive electrode through an electrolyte. And we have ionic exchange. That is the simplest part of the lithium-ion battery. But the complexity is depend on the redox couple that we can build. As we can see in the anode-based, low voltage-based material, we have like several kinds of materials like lithium metal, carbon, silicon, LTO, and for the cathode positive electrode, we have different family. And depending on the redox couple that we will build, the problem will be different, the phenomenologies will be different, and the process will be different. So there is many parameters that link the capacity loss of the chosen system to the performances. One of them is the loss of capacity related to the redox process, the loss of capacity related to the SEI growth, the loss of capacity that could be related to structural change, and so on. And XPS can help to probe several of those techniques and in different way. XPS can act in the beginning of the process. For example, we can characterize the pristine electrode or even the pristine materials. So we can assist for synthesis to see if the material that we synthesize, it's like suitable, it's like fit to the requirements that we fixed in the beginning. So we can have information about the local chemical structure, oxidation state. During cycling, so we can probe the lithium insertion, extraction, and through the redox process or the solid electrolyte interface growth, or nowadays with the growth of all solid battery, for example, we can that can help to understand the interface in hybrid electrolyte like polymer ceramic or the interface between solid electrolyte and electrode. And in all those cases, we need to have very careful sample manipulation. And this is how we deal like this, like the XPS nowadays, it's like we have many research that's moved to operando XPS, but today I will just like talk about XPS in post-mortem analysis. What does mean post-mortem analysis? That means we will mount the battery, we will cycle. In this case, we are showing the charge curve of lithium insertion in graphite. This is the first galvanostatic cycle. And what we do, we will stop the battery at different cutoff potential. We will open it in the glove box. So we will do some chemical surface treatment like washing with solvent or not, transfer the sample to the XPS and do analysis. So for that, we have to need very careful sample manipulation. Either we need, as I shown here, a glove box, either some laboratory, they connect the glove box directly to the XPS. It's not our case because we do not like this option. Or we can develop some transfer vessel that can help to transfer the sample from the glove box to the spectrometers. We can also make some pre-treatment by mechanical scratching, ionic etching, or other kind of etching, or we can analyze the sample at low temperature, for example, for liquid phases or polymer that are sensitive to the X-ray beam. Here, after this first overview, I will give the first case study is the lithium reactivity toward electrolytic media. Here, I will give you a first example. It's like this is electrolyte based on ionic liquid. What does mean ionic liquid? Is molten salt at room temperature. Our ionic liquid is based on cation, which is imidazolium-based cation, and two kinds of anion, TFSI and FSI. In this case, the electrolyte, to make it electrolyte, you have to add salt. The salt in this case is RiTFSI. Here we can see that the reference sample XPS, before adding the salt, is the above spectrum. This is the carbon peak of C1C6 im FSI, that means C1C6 with this kind of anion. C1C6 im TFSI is with the second kind of anion. We can see that the XPS here, the carbon peak has two signatures. The first one is the carbon related to the alkyl group. The second one is the carbon related to the aromatic ring. When we add, for example, the salt, RiTFSI, we have a new peak appear, which is related to the CF3 group in the TFSI. So here we can see that the carbon peak can give very accurate information about our chemical structure of the materials. That is regarding the carbon peak. If we look at, for example, the nitrogen peak, which exists at the anion level and the cation level. Here we can interesting that we have two nitrogen in the cation and one nitrogen in the anion. What we are looking here, that we have two intense peak. One has 2 times the intensity of the second one. So the first peak is the anion related peak, and the second peak is the cation-related peak. So here also we can quantify in molar ratio our composition. So the XPS can also give qualitative analysis about our electrolyte and also quantitative analysis. What is interesting that the chemical shift or the energy difference between both peaks can be related to the interaction between anion and cation. And we could build some model here depending on the delta here, the difference between cation and anion energy, and we can link that to the interaction, the coordination between anion and the cation. More the coordination is weak, more the delta is higher. So that also can give some information about charge delocalization in this system. The second part here, we studied with collaboration with other academic partners, the reactivity of lithium toward these two kinds of ionic liquid, and we measure the impedance at symmetrical cell, and we can see how we age those cells at room temperature. And we can see the evolution of the interface resistance and bulk resistance during cell, and we can build some by recording the electrolyte resistance and the interface resistance. We can, depending on the nature of the salt and the electrolyte, we can see some modification. What we can see that we have different behavior of the interface resistance during time. That means I will not go in detail. I would just like to emphasize that how we can link electrochemical information to XPS information. So the main conclusion here that this lithium surface reactivity toward ionic liquid in all cases, but this reactivity is less when we use FSI-based ionic liquid. And when we add salt, like for example here, I give the case of C1C6 IMT-FSI, we have degradation upon time of this kind of lithium surface for this kind of electrolyte. But when we add LiTFSI to this kind of electrolyte, the electrolyte resistance becomes stable. That the salt plays some role, and we will see later how the XPS can explain this can link to this kind of information. So we performed XPS at the surface of lithium metal after aging. The first spectra is the nitrogen peak of different kind of combination, electrolyte combination, C1C6 IMT-FSI without and with salt, C1C6 IM-FSI with and without salt. That is the pure electrolyte without any reactivity. Okay, after aging during 10 days, what we can see here, for example, for C1C6 IMT-FSI, that's the cation peak decrease and can be linked to the increase of the resistivity during aging. When we add salt, the peak remains stable, can be linked to this stability of our system. And this is kind of TFSI, but in case of FSI, we have less degradation, which can be linked to the stability of this kind of electrolyte. We did the same thing for fluorine, for example, because the fluorine is one of the components of our electrolyte. And we can see, for example, for this kind of combination, we have degradation of this LiTFSI-based electrolyte with the formation of LiF, which is the case for other electrolytes, but in different proportion. So from this analysis, we can understand that the LiTFSI can decompose to form LiF of lithium nitride or polyoxysulfide. And also we can emphasize that there is a degradation of cation when we have less LiTFSI in the system. So the degradation of cation can induce anionic decomposition. So this study, based on some reference study, like performed by Orbach and other group, that they explain some mechanism of anion and cation decomposition, we can build some SEI model of the surface of lithium during aging in different electrolytes. So if you want more about this study, I invite you to read those papers. The second case study is the redox process. Now I show you how the SEI XPS can give information about this, the SEI growth or the activity of surface. Now I will move to the redox process. I will choose the case of lithium titanium sulfide based batteries. This is our electrochemical system is lithium with EC-DMC LiPF6 electrolyte and the cathode and the positive electrode is titanium sulfide. And this is our galvanostatic discharge and charge curve. So what we did, we cycled our coin cell and we stopped it at different cutoff voltage. And we opened the cell, as I explained before, in the glove box, and we transferred the XPS, and we acquired XPS spectra at different voltage. Since we have titanium and sulfide, so we will probe both atoms, the titanium core peak and the sulfide core peak. So this is the starting point without any insertion. Before insertion, we can see that we have two oxidation states of titanium and two oxidation states of sulfur. We have sulfur 2- and disulfide 2-. When we start insertion, I mean after 0.8 lithium insert, we can see that the system almost, we have an increase of S2- contribution, but the titanium do not move. There is no change for titanium peak. At 2.7 volt lithium inserted, we can see that the second sulfide group disappeared and only the sulfur appeared. That means we have preferential reduction of sulfur. Up to now, the titanium do not move. At the end of discharge, the whole sulfur was reduced, but in the meantime, titanium was reduced. When we charge, we have titanium is oxidized and keep oxidizing, and the sulfur, it's oxidized, and we will go back to our original spectrum. So that means we have a reversible redox process, but we can quantify the amount of electron that exchange from the beginning to the end of charge. So we could, from the XPS, follow the redox process through the whole galvanostatic curve from the beginning, during the discharge and the charge. And also nowadays with the NMC, XPS can also help to quantify different grade of NMC. Like here I give the nickel peak in NMC 532. That means we have 0.5 nickel, 0.3 and 0.2 cobalt, and etc. So here also the XPS can help for this kind of technology. Here I will go to the third case study, is the band gap engineering for battery technology. So I will give the example of RTO, lithium titanium oxide, Li45012. As we know that LiTO is material that's from the literature that is SEI-less growth because it's work at 1.5 volts above lithium voltage. So in this case, this material is characterized by a plateau, which is like corresponds to the biphasic structure when we can insert 3 lithium, and we can move from phase Li4 T5O12 to Li7 T5O12. And usually for these materials, we have to use a binder, like ore with black carbon to make it conductor. But in this case study, we did some surface treatment to these materials. So we do not need any more carbon to cycle these materials. And it's interesting here, as you know, LTO has white color. That is our pristine materials, electrode. And when we cycle, the color change to blue and become, at the end of discharge, become black. When we charge, we get back our original color. That means we have certain redox process. We move from semiconductor materials to metallic-based material. That's why it's become black, and it's quite reversible. So we don't need any black carbon to help this material to work, just by surface engineering. And And in the XPS, we follow the redox process on titanium 4+ and 3+ during the first discharge and the charge. And we can see here, that is the initial point of titanium 3 peak. We have mainly 4+. When we discharge, we have reduce of the intensity of titanium, and suddenly at the point D and C here in the middle of the galvanostatic discharge and at the end of discharge, the titanium is not observed anymore. How can we explain this? I didn't say before that the XPS depth analysis is 5 nanometers. That means we do not see titanium anymore. That means it's buried beneath some thick layer, which is at least thick, like 5 nanometers. But when we zoom in this area, we can still see some titanium. What does mean? That we formed some SEI at the surface of the material that's with a thickness of at least 5 nanometers thick. But what is interesting, that when we charge, the titanium appear again, which means that this SEI was dissolved. That's why for many years, LTO was considered like SEI free, but in fact, the SEI is formed during charge and is discharged and is dissolved during charge. Just when we do post-mortem, sometimes we do not observe this phenomenon. And to understand the chemical structure of this SEI, that we will probe the oxygen and carbon peak during at different states of discharge and charge. And what we see here when we probe the carbon, that during discharge, we observe the presence of some alkyl lithium carbonate group and the presence of Li2O when we probe the oxygen peak. And during at the end of the charge, the lithium carbonate peak disappear, which is confirmed the dissolution of the SEI. Some TM analysis has proven this process, and we can see that at the top of RTO, we have some thin layer of SEI, which is about 5 nanometers. So the XPS finally can give some order of magnitude of the thickness of SEI without any, and the good things here that the XPS is non-destructive technique, that we don't need to prepare the sample like in TM. TM, we have to make thin film and we have to wash the sample. That need advanced preparation, which is not the case in XPS. And from this claim here, we can imagine some chemical reaction that explain the process of formation for lithium carbonate. For example, the decomposition of EMC, ethylene methylene carbonate, through bioelectronic process to form methyl carbonate with some degassing, or through monoelectronic process to form lithium carbonate. So that could be one of the reaction that could be at the origin of this peak that we observe in the carbon. And now I will come to the new development of XPS, like depth analysis. In XPS, we can do depth analysis in different way. Either we can change the angle. That means we will change the angle of the photon through to the surface. I will go back to see. More we go to raising angle, more we probe the surface. But the problem in this case, when we probe the extreme surface, the count rate becomes low. So we need to acquire for a long time. There is another way, is to use different wavelengths. So we can use a photon with 130 eV, 100 eV, for example, and more we enhance the photon energy, more we go deeper. For example, that's why I said with XPS nowadays, we can use XPS to understand, for example, the chemical structure on silicon-based battery by changing the photon energy. For example, here, this is silicon oxide cathode with a silicon bulk cathode with a silicon oxide native oxide layer. And by changing the energy, we can probe deeper. And by this way, we can, when we form the SEI, we can follow the thickness and the composition of the SEI at different states of charge, just without any sample preparation or etching. So this is another way to probe deeper and evaluate the thickness and the composition of the SEI using modulated or like photon energy. The second way of depth profiling is what we call ionic depth profiling. Here, there is two kinds of depth profiling. There is either ionic depth profiling or gas cluster ion depth profiling. Here is the ab initio, like a dynamic molecular simulation of two kind of ionic sputtering. This is monoionic sputtering. This is boron atoms that is accelerated to 20 kilovolts in some kind of sample. We can see that when we do etching, the boron will penetrate deeper in the material with lots of cascade interaction. So that will generate chemical damage of our sample. And sometimes we do not need that, because especially if we want to keep the chemical structure or the oxidation state of our material unchanged. We can solve this problem by using cluster. Instead to etch with ions, we will etch with a big cluster, which is composed of thousands of atoms. So in this case, is more soft and is more surface etching. We have two different kind of cluster. We have like C16 kind of cluster, but in this case, which we call Buckminster-Fuller atoms. But in this case, we will reduce the chemical damage, but the problem, we will have carbon implementation, especially if we want to probe the carbon-based material that can give some artifact. The second way of ion GaN, or cluster ion GaN, what we call gas cluster ion beam, in this case is suitable, but it's need a lot of adjustment because we have different recipe that we have to adjust. But this is more powerful for polymer-based materials. I will give an example. Here I give an example of a P.PSS, which is not battery material based, but is solar cell based materials, which is used as for heterojunction, as solar organic photovoltaic cell. And we use, we make stack of PSS, PSS and P dot deposited on, we deposit PSS and P dot, and on the top we deposit like a polymer, graphene-based polymer, graphene-based structure, sorry. And we use two kinds of depth profiling, ionic depth profiling and Gcib depth profiling on the same sample, just to show you how the damage is when we use ionic-based depth profiling. Let's start with Gcib. With Gcib, when we sputter, we have two signatures of P dot and PSS. We have, when we look at the sulfur peak, we have two peaks. And when we etch, well, in fact, we will etch few minutes and we record XPS spectra. And we can see that the signature of P dot PSS remains stable. We do not have any change in the chemical structure. But in the case of ionic-based beam, we can see that we destroy completely the PSS structure. That means this kind of sputtering, its damage can provide some damage to the sample. So we should be careful when we do ionic sputtering, especially for battery-based materials. And also when we can see here, if we do quantitative analysis, depth profiling quantitative analysis based on Gcib, we can see that we have the pentacene group, sorry, it was pentacene here, and the P dot PSS. So we have very nice depth profiling, and we can follow the concentration of carbon, oxygen, sodium, and sulfur of our materials. But in case of ionic-based depth profiling, our depth profiling is completely useless because we lost lots of information, especially at the interface. The information at the interface was lost. So just this is a takeout message. Please be careful when you do ionic depth profiling. And also this can happen also when we do tough sims or we do focused ion beam, especially for polymer-based materials. And this is like, just like I'm coming to the end of my presentation. XPS is almost 60 years of development and was like used for different field of technology, semiconductor, heterojunction, battery technology, 2D materials, catalyst, heterojunction catalyst in everywhere, and also some contrefaçon, like making like to probe if the materials are fake or not. So there is like just an example. And just like takeout message, XPS is non-destructive technique to probe the chemical and the electronic structure of materials. It's need either like very simple interpretation or like advanced interpretation through ab initio calculation. We can detect all elements except hydrogen and helium. We can get atomic concentration. This is the the sensitivity of XPS is 0.1 atomic percent. We can perform depth analysis either by angle result or ionic etching or gas cluster etching. And I didn't show you this example. We can do also 2D chemical mapping. We can do like map the chemical structure through a 2D mapping. And XPS within TEESMAT framework. That is the, I was like talking with Agatha, and in this case, I will not show the result because some partner, they will not accept that. But at least XPS was involved in 5 user cases, and like Gcib, Synergy, Arkema, and Umicore and UNESCO. And in every cases, we have different problems. The first one is was copper metallization of polymer substrate. The second one was aging of printed electrode and see some gas evolution in the reactivity through electrolytic media. Arkema was like separator case. Umicore is like their cathode materials, and UNESCO was like the ACI growth at the beginning, middle, and after of life of electrode evolution. And thank you very much for your attention. And if you have a question, I hope it was clear.
Thank you, Anass, for this session. Very nice presentation and also very, very interesting. Thank you. If some of you has any question, we can collect the questions, and Anass will be happy to reply to them. Is there anyone? I think no one shared anything in the chat. Bye, Jérôme.
Bye, Jérôme.
Okay.
So at least maybe I can have one for you. So if there is nobody that no, okay. So at least it's Anass. Thanks for the presentation. But when you were saying that, for example, you are checking the oxidation state, in the different element, I would say, when you are doing this, of course, XPS is 10 nanometer or something like this. So, and additionally, there is a SEI. So do you have a strategy, let's say, to tackle this in order to trying to understand if this oxidation state is related, can be related to bulk or?
Yeah, indeed. It's a really good question. Anyway, we have 2 strategies. The first one, when we have like composite electrode, that is protocol that we developed several years ago, that we can scratch the electrode in the glove box with some knife, just a little bit scratch, and then we can analyze the blood. And then we can analyze before and after scratching, because we can easily find the area. And usually we have made several studies, and we can see the difference between surface and the bulk. Of course, when we do that, we don't know how much we scratch, but at least we know that we are in the bulk. That is the first strategy. The second one, we can use, for example, ionic etching, but as I showed, the ionic etching, we should be careful with that. Or we can do gas cluster ionic beam etching. That also could be, but needs some development of methodology. But in many cases, as you know, in battery, it's a matter of surface potential as well. And the reactivity of the surface is also important. But anyway, there is a strategy, but those are the main strategies that we use.
Okay, thanks a lot.
Welcome.
Okay. Any other questions?
Hello, this is Dimitrios Zarvalis from CERT.
Hello.
Thank you, Anass. It was an excellent presentation. We learned a lot. I just wanted to ask a simple question. I mean, you said that at the first time that you will only present XPS for post-mortem, but this you could also use in situ measurements. Is this right? And
Yes.
how much more difficult is in situ measurements? Because I understand for ex situ and post-mortem analysis, you need to cycle coin cells or other cells and then cut the cells at certain voltages or state of charge and open them. I mean, isn't this more difficult than in situ analysis, or how do you treat that at the CA?
In fact, in situ analysis in XPS is quite challenging, and there is only few works nowadays. We have performed one. I mean, there is like two problems to solve. The first one is ultra high vacuum. That's we have to find some battery that work in ultra high vacuum. As you know, or volatile electrolytes do not support this kind of system. But at least we can do operando for all solid battery or for ionic-based electrolyte, because ionic liquid have low vapor pressure. And this is the first challenge that we have to solve. The second challenge is the geometry of the cell, that we have to build up a cell that should be represented, that should have very accurate electrochemical response, because we should know, it's not just like by connecting two cables and we say that we are doing operando. At least we should have very accurate electrochemical response. That is the second one. And for that, we have to build up new cell, like to make this geometry. So here in the lab, we perform few works like this. We have some knowledge on that, and we published a work. I can, if you want, send you the paper, and you can see what kind of, how can we deal with that, and what is the challenges. But there is only few works, and this still in the, I mean, in the, how can I say, if I have to say, it's the early age of operando for XPS. Not like Raman or XRD that they make lots of advanced. I mean, for example, XRD, it has been like 30 years and they make a lot of progress. XPS is we just started this kind of methodology.
Okay, thank you.
Welcome.
Okay, any other questions? Okay, unless anyone has anything else to add, I think that's it for today.
I think either I was clear or I was like boring.
No, it was very, very interesting, Anass. I would like to share with you, just before we go, a link for our website. You can follow us and you can receive all the updates about our webinars, because today we had the first one, but we will move on with the next ones. And actually, I can already tell you that on the 8th of July, we will have our second TEESMAT webinars. It will be presented by Incor System, and it will be running at the same time as today, so from 3 to 4. Okay, here is the link to our website, and you can also follow our social media pages. We have LinkedIn here. The link.
Hey, can you see all of? Because I'm sharing the screen. They can see maybe.
Yes, you are sharing the screen, and I put the links in the chat.
Okay, maybe they are. Everyone can see the chat. Okay.
Okay.
I don't know if it's good.
Okay, I think that's it. Do you want to add something, Anass, before we close this session?
I think no. It's thank you for everything. It was a nice experience, and hope that
thank you.
TEESMAT will have a nice synergy, and I mean it's nice synergy in this project, and it's good. And thank you for the whole people that's working in this project and trying to make it work.
Thank you very much, and thank you everyone for joining us today. Have a nice afternoon. Bye bye.
Okay, goodbye. Thank you,
Okay,
Anass.
bye.
Thank you.
Thank you. Bye.